All right, so yeah, I guess it's 5, so we can continue with Muhammad Harun Ali Khan, who will talk about formalizing some Diophantine results, right? Most notably determining all the squares in the Fibonacci sequence. So yeah, please go ahead.
Right. Hi, everyone. So today's talk is about a result we formalized in Lean. You know, the squares, there are only finitely many squares in the Fibonacci sequence. And in fact, we know exactly which ones there are. It's 0, 1, and 144. And so another way you can say this result is 144 is the largest square in the Fibonacci sequence. And okay, so we formalize this result in Lean. And I use proof by Khan, so that's from the 1960s, a paper from the 1960s. So first, let me just define these sequences. So we use a set of natural numbers including 0, so that's how natural numbers are defined in Lean. And then we define the Fibonacci and Lucas sequences as shown. So I mean, the first term is 0, and then the 0th term is 0. The first term is 1, and then you have this recursive relation. And then the same thing for the Lucas sequence. You know, but 0th term is 2, and first term is 1, and you have the same recursion. And then, so the main theorem we're formalizing is exactly the following. So if you have a Fibonacci square, then the index could only be the index of this Fibonacci number can only be 0, 1, 2, or 12. And so these corresponds to 0, 1, and 144, right? For F2, it's also 1, right? So, and as I said earlier, we implemented Kahn's proof of this theorem. You can find the project here. And now let me start talking about the formalization. So in the paper, the proof is broken down into 3 parts: preliminaries, some you know, identities we need to formalize, some lemmas, and then facts about the Lucas squares. So actually, we have a similar statement for Lucas squares as Fibonacci squares. There are also finitely many Lucas squares, and we use that to prove that there are finitely many Fibonacci squares. All right, so let's give an outline of the proof. So first, in Kahn's proof, he extends the Fibonacci and Lucas sequence for negative numbers using the recursion. So like, for example, so he's extending to negative numbers. So for example, if I go back here, you can figure out what f of -1 is. You just need f of -1 plus f of 0 is equal to f of 1. So f of -1 turns out to be 1. Right, because 1 plus 0 is 1. And then you can also extend the Lucas sequence to negative numbers as well. So that's what they did. And then they prove 2 theorems. The first one is there are only 2 squares in the Lucas sequence. That's 1 and 4. And the second one is if you look at 2 times a square in the Lucas sequence, then the only ones are 2 and 18. Because if I divide by 2, I get 1 and 9, which are both squares. Right, so we need to prove these 2 to prove our main theorem about Fibonacci squares. And here I'll outline the proof of theorem 1, which was the only Lucas squares are 1 and 4. So these are the main identities we formalized in the preliminaries that lead to this result. So I mean, for the first one, actually, this just shows you that there can't be any a Lucas square with even indice, because even index, right? Because I mean, that would imply that the difference between 2 squares is 2, but that's impossible. So then we're left with considering just the odd Lucas terms, and now here's an interesting argument that's used in every single theorem after this. So it's used to prove Fibonacci squares as well, and a similar argument, and it's used to prove the double Lucas squares as well. What you do is you notice that L1 is a square, and then you take M as 1 mod 4, and you can write you can decompose M as follows, right? And then you can use property B to get this relation, because okay, the k is supposed to be inside the parentheses, right? Because we just use this applied to m here, and we get Lm is negative L1 mod Lk. But here's the problem: Lk is 3 mod 4. For any even integer k not divisible by 3. Here we made sure k satisfies those properties. That's why we did the decomposition. So we know here Lk is 3 mod 4, and that's a problem because that would imply, L1 is 1, right? So negative L1 is negative 1. So this is negative 1 would be a quadratic residue, mod Lk, but Lk is 3 mod 4. And, that can't happen because negative 1 is never a quadratic residue, a number mod that's 3 mod 4. So that means you can't have squares, you can't have any other squares in the Lucas sequence. All right, and as I said, so interestingly, just want to make a quick remark here. It's like the existence of L1 prevents other squares from existing. Okay, so and then you use the same idea for the proof of theorem 2, which was, the statement about the double Lucas squares. What we do is we find a square. You look at residue classes mod 8, and then those classes mod 8 that have a double square in them can't have another square because of the same argument from before. It prevents other squares from existing in that certain residue class. And then you can use, the same argument before that negative 1 is a non-residue modular number that's 3 mod 4. And then finally, we have theorem 3, which is the main theorem about Fibonacci squares. And it says we do the same thing. If n is 1 mod 4, then f1 is a square because it's equal to 1. And use the reduction argument. And here I'm referring to that argument we just talked about as the reduction argument to prove it's impossible to have any other squares when the index is 1 mod 4. And if n is 3 mod 4, then you're done, because so now you have fn is f of negative n, right? This is if we extend the Fibonacci sequence to negative indices, then we have this relation. So this implies negative n, because n is 3 mod 4, the negative n is 1 mod 4. But then we already proved that the only square that's 1 mod 4 is 1, right? Yeah, the only index is 1. So this just gives you f of negative 1 is also a square, which is essentially f of 1 as well. Now the last thing is even. So this case is harder because if you notice, the odd case is similar to what we've been doing. We didn't use theorem 1 or 2 yet, so we're going to use it in the even case. And we proved something in one of the preliminaries that an even number, f of an even number is the product of the Lucas term and the Fibonacci term. And you also proved that the GCD between the Lucas terms and Fibonacci squares is at most 2. So that's really nice, because now you have the GCD between the product of between these two numbers is small, and the product is a square. So you could you take several cases. Either the GCD is here or it's here, and in other words, these terms become the GCD times a square, right? One of them must be a GCD times a square. So and then we drop back to theorems 1 and 2, and we get the result. Right. So now let me talk about our formalization and of the preliminary. So we formalized, these were 13 identities, and but there was also a lot more. Sometimes you need to do a lot more than just formalize the preliminary right away. Sometimes there's some prerequisite results. So for example, to formalize some of the recursions, we need to formalize some other recursions first that are useful in formalizing later ones. So for example, the Fibonacci-Lucas relationship, which is written here, or another form of it. And we also had just some proofs, some lemmas that shortened our proofs. Like, for example, if you have two natural numbers and m is smaller than or equal to n, then you can write m as k plus n plus 1, where k is also a natural number. And this just helps to go through the base case of induction very quickly. There could be a better way to do that, but this is how I settled on doing it. Okay, so now let me talk about some formalization problems I faced. So first of all, as I said, there were many identities in the preliminaries, and so we could use the Fibonacci and Lucas closed forms, right? But now the problem is those involve like some irrational numbers. In fact, like 1 divided by the square root of 5 and golden ratio and so on. And these are not easily. It's not easy to manipulate these in Lean at all. So and not efficient either. So for example, so instead we proved all of our identities with induction, sometimes two-step induction, mostly two-step induction, because you can describe a new Fibonacci term in terms of the two earlier ones. So that's why we always use two-step induction, and then so to formalize this identity, for example, it just takes seven lines of two-step induction, which is quite short, right? So that's I mean, you can just do induction on n, say, and then you have the relation. The proof just follows. Right. So the next problem is integers. So so in the paper, they use extensions of Fibonacci and Lucas to all integer indices, like the negative ones too. But I define my sequences from the natural numbers to the natural numbers, so without it didn't extend. And the reason is because it would be difficult to go back and forth. We have a lot of natural number theorems in our library, which we wanted to use, and if everything was in integers, you would have to deal with all of these maps between integers and natural numbers, and you'd have to alternate back and forth, which would make the proof longer, the formalization longer. So I decided to what I decided to do was let's just stick to let's not extend to integer indices, and let's modify the proof of Cohen's paper a little. So where exactly did we use the fact that these are integers? Well, we only used it in the proof of theorem 3. When we said, if I go back a bit, when we said when we said Fn is f of negative n, and then we fall back to the case n is 1 mod 4. So I added a few lemmas to compensate for this, and basically for some identities, instead we formalized an addition version of it and a subtraction version of it, because if the identity is for all integers, then it's like separately. If you take them as positive non-negative integers, then there'd be two versions. One is addition, the other one is subtraction. So for example, here's one such identity. You have this relationship, but instead we formalize the following. So 2fm plus n, so the same thing, but now notice that mn and k are natural numbers, and before they were integers. And then and then we also formalized, which is essentially the subtraction version of it. And you get this, right? And here you have -1 to the power n. Okay, and then to deal with these -1 to the power of something is quite easy. Just you can use some AI tactics like normcast or ring, for example. Okay. Right now, all right. So now let me talk about our formalization of Lucas squares. So remember, as I said, we wanted to show that the difference of two squares is not 2, right? And that would imply there are no even Lucas squares. So you could do this in two ways. I thought of. You could use inequalities, and you could use quadratic residues, mod 4. And it turns out that for formalizing, quadratic residues mod 4 is much better because you can just you can just have simp or ring solve all of the cases automatically. What it would do, it would just check, you know, it would put 0, 1 here, 0, 1 over there, and check 0 plus 2. For example, 0 plus 2 and 1 plus 2 is not a quadratic residue. So with mod 4, it's very quick. On the other hand, with inequalities, on paper, maybe the proofs are about the same length for inequalities, but it's a little bit tedious to formalize because so we use the proof with quadratic residues. That's one example. Another lemma I formalized for the Lucas squares is that every number has a maximum power of 3 that divides it, and it could be 0. So, and how we did this was a little strange proof. So use contradiction and induction. I mean, so if you use contradiction, then suppose you know, R can be as large as possible. I mean, you get to a statement like if 3 to the R divides n, then 3 to the R plus 1 divides n, and then you know, that leads to you can, that's kind of like an induction statement, and that using induction, that implies 3 to the n divides n, but clearly 3 to the n is much bigger than n. So, for example, on pen and paper, this is just something that's so intuitive. We don't even think about. We maybe don't think about it for a second. But in Lean, everything has to be formalized, right? So even the fact that this R exists, we have to show it. And then finally, here's one lemma that was interesting to formalize. So -1 is quadratic residue mod n implies n is not 3 mod 4, right? In other words, if you have a number that's 3 mod 4, then -1 is a non-residue. And what we did was, so what's the pen and paper proof? It's once again, it's like consider the prime factorization of n, and so suppose, let's just say, suppose n is 3 mod 4, and you take the prime factorization, and one of those primes must be, -1 mod 4, because n is 3 mod 4, right? And then we already know that if you have a prime that's 3 mod 4, then -1 is a non-residue by some Fermat's-Little theorem. So fortunately, the statement about primes was formalized already in this library, number theory.quadratic reciprocity. So I just had to, I had to mimic this proof, but it's actually, it's a little different from the paper and pen proof. Like on paper and pen, we just say consider a prime factor or something like that. But in formalizing, instead we used strong induction. So what we did was we take a prime factor of n, and there's a lemma in one of the libraries that allows you to, you know, take the smallest prime factor of n. All right, so then, and then you have, you know, n is a product of, like, you know, some p times k, and both of these are smaller than n, right? So you can use strong induction. And so that's how I did it. And then when you use strong induction, then it just boils down to checking, you know, -1 is a non-residue mod p, and it's a non-residue mod k. So it's non-residue mod n. All right, finally, so we get to the last result, which is about Fibonacci squares. But even before proving Fibonacci squares, we had to prove another lemma. Is that if you have the product of two numbers as a square, then you know, both of them are GCD times another square, right? And to prove this, I actually just prove the case when it's co-prime first. So if you have the product of two co-prime numbers as a square, then both of them are going to be a square. And once again, you guessed, we're going to prove it by strong induction. And the proof, I'll just illustrate it here. So let's take prime p that divides a, then p divides you know, a times b. So p divides n squared. So that means so we have this lemma, right? a prime divides a square, then it divides n, right? And so that implies p squared divides n squared, right? Because p divides n, so you can square both sides, you get p squared divides n squared. And then, so you have p squared divides the left-hand side, so, and p already divides a, so p cannot divide b. So you can show this by contradiction. You can say, if suppose p divides b, then, then the GCD between a and b won't be 1, right? It would be p, at least p. So, so then you have the GCD between p squared and b is 1, and then you can use this this lemma that you get a p squared divides a, and then n over p squared is a square, so n is a square. So I mean, so p squared divides b. The GCD between p squared and b is 1. So and then you can just induct downwards, right? Because this is a square, so and then the remainder is also a square. Right, then when you prove this for coprime numbers, then the statement above is just a corollary of that. And it's an application of this one. So it just follows. Right, so so that, and then after we prove this, so the reason why we need to prove this is because we have the statement about the even terms are a product of two, a Lucas term and a Fibonacci term, but the GCD between the Lucas term and the Fibonacci square is at most 2. And so we have that situation. You have a square as a product of two numbers, and the GCD is, you can take two cases. If the GCD is 2, then this is 2 times the square, and so is this, right? But then you already know, exactly know what Lucas terms are 2 times the square, right? So we're done with that case. And if it's if the GCD is 1, then you have this is a square and that's a square. But you already know which Lucas terms are a square, so you're done with this case as well. And right, so that completes our formalization of the Fibonacci theorem. I think just some final remarks. I think it was quite remarkable to see Lean handles the high-level arguments quite nicely. So, like for example, the one about quadratic residues. Let me see if I can find it. Right. So part C. This is like one of the non-trivial, non-element. Well, it is elementary, but it's one of the non-trivial lemmas, and it's one of the main lemmas. But actually, it was handled very nicely by just piecing a lot of lemmas from libraries together. So these, Lean was, it's very good at these high-level arguments. And as, on the other hand, so sometimes the inequalities or the algebraic identities, those are quite tedious, but the high-level arguments are somewhat smoother. So, like for example, even this part was just very nice and lean. Although it could be said that this is somewhat like harder than proving some inequality between two squares, right? Okay, so so that's all, and right. If you have any questions, you can ask now.
All right, let's thank Mohammed. And indeed, any questions or comments?
Is the Lean code available online somewhere? Yes, it is actually. I mean, there's the link. Yeah, it was. Here's the link. I mean, let me try to paste that in the chat. Okay, but I guess you can just type GitHub Fibonacci squares on Google, and maybe this can show up. Yeah, thank you.
All right, the link is in the chat now. Adam?
You mentioned that you managed to find some lemmas that shortened your proofs. I wonder if that was done during generating the proof or just as a kind of refactoring with the existing proofs.
So yeah, that's true. It was found like during generating the proofs, like when you formalize, you realize some things are being used a lot of times in different results that we're formalizing. So to make everything shorter and more efficient, you just formalize one result. Like I'll give you an example here. Like for example, this one. So I realized I had to verify base cases for induction a lot of times. So after doing it 3 times, I just decided to let's make this lemma, and then every time we need to do it, we can just quote this lemma, and yeah. So it was many of these were just found during the proof. Like for example, another example would be the one about powers of 3. So initially I thought this should be, I mean, every number has a maximum power of 3 dividing, and so I thought this wouldn't be a problem. I didn't see it beforehand, but then when I got to this stage, and where do I use this? I use it when we try to decompose in one of the, decompose m as this 1 plus 2 times d to the r times k. And I realize this needs to be formalized because how do we know r exists? Yeah. So normally the first step would be to check the library if there's some statement, but number theory has so many statements, so many of them are not in the library, and so yeah, so we had to formalize it. So yeah, I'd say it was yeah.
Sorry, I just wanted to comment that it shows that you indeed was creative during writing the proof, because some people claim that formalization kills creativity. So people just use what others have already done, and they just put this into computer and so on. But your case shows that you can still be creative, and that's a great thing about formalization that not many people think about. So yeah, it not only helps you just keep track of the proof and record the proof, but also give some more insight into it. So that's a nice example.
Exactly. I would say definitely in the case of this theorem, there's a lot of there's a lot of it wasn't standard, I'd say. Like we could only use the library like not that many times. Most of the results had to either come from the paper, or I have to think of some like connecting results between what you understand and what's in the paper, right? So, and then it also helps you understand it much better, the mathematics. Some of the results you take for granted, but then when you actually try to think about the proof to formalize it, you get to know the proof of the theorem to a more deeper level, right? So yeah, there's definitely a lot of creativity involved, because the library doesn't cover it didn't cover a lot of things. We had a lot of things we had to formalize separately. Even for example, this one, I looked for this one in the library, but I just couldn't find it. And maybe it's in the library. I was a little, yeah, it's a little surprising, but yeah. So creativity is.
It's sorry.
Yeah, sorry. It's mainly from the fact that sometimes you need to change a proof for formalizing, change an argument like we did for integers or closed forms, where sometimes you need to decide on what to formalize before you could formalize this key lemma. There's some things that need to be done first, and they're not written in the paper, and so you have to figure out what those assumptions are first, what those lemmas are first.
So I just think it's not so nice about Lean at that moment, that you really have to choose between this closed form with square root of 5, for example, and not being able to just smoothly switch between natural numbers, integers, and reals, and so forth. So I'm just thinking about the possibility that we have in Mizar, so that all those numbers doesn't need any kind of coercion, mapping, or whatever. You can just treat them as complex numbers or real numbers or natural numbers, and this is a natural mathematical property that's very nice to have in the library. So I just hope that Lean's library is also developed in this direction, that this kind of easy reuse of facts common for all kinds of numbers is just possible.
I agree. The coercion is somewhat a bottleneck. It makes a lot of proofs very tedious. Like as I said, some of the later proofs that are a little bit harder to for our human brain to comprehend are actually handled much better in Lean, because like this one, for example, this one doesn't involve any coercion or anything like that. So Lean just puts all the pieces together very efficiently, very nicely. And it's like, I'd say, a more high level argument. Yeah, but some of the, for example, proving like some inequality like that, either you're left with a lot of, cases to check, or there's coercions. So yeah, I agree. Those take longer to formalize than these high level arguments.
All right, I thank you very much. I propose we continue